Okay, hi. This is just following up on stuff that I missed or didn't mention. Um, let's. Oh yeah, the previous video is loading to YouTube. Exciting. Let's maybe start a new Bitly. Hide this thing. Okay, so we kind of got up to this idea, this KAKB. I think I said we would explain it. Let's see if we can jump back maybe here and see what these are. If I multiplied that by this, would it magically reduce? Yes, CH3COO is on the top. Aha, let's write that out. Brilliant. That's so great when things work out. So if I write out Ka, what's Ka again? Products of reactants. So it's this thing, H positive, and then the acetate ion is the product, C3COO, all over CH3COOH multiplied by CH3COOH, and then the other product to that is OH minus all over the CH3COO minus thing. No, so they all, I think, they will all cancel. This is going to cancel with this. Concentration of that and that. And Shazam, what are we left with? We're left with this business. We're just left with the H positive. Hi.
Hi.
Do you want to be in a video?
No, but I
Great.
haven't heard back from him yet.
Trentus?
Yeah, and they're on screen.
Okay. Stop him.
Okay.
Hi guys. Domestic. Okay, so then we get down to we're left with these, right? And so Ka times Kb does equal that. So I hope that answered one of the questions that there was about this. Let me take a moment to think about what. Oh yeah, I think we were going to talk about looking at, say, oh, I remembered the other strong acid. It's chloric acid, which is HClO3. I guess this thing is so stable. This ClO3, this chlorate ion thing is so stable that it just does not go back. It does not steal a proton off of water or off of a hydronium ion if it bumped into it. So yeah, like this does not do this. When it hits water, it is not able to steal anything from it to go back to the HClO3. That doesn't happen, right? When these have a tug of war, this wins, right? That's why it won before, because it what did it do? As soon as the HClO3 hit the water, that happened. Plus ClO3 minus. So we can kind of look at, well, why is that? So why is that so stable? So let's kind of look at what we know. We know that, well, you should know, HClO is very weak. Goes to H positive and then the ClO minus ion, and then HClO2 also weak. O minus and this has a Ka here of 2.9 times 10 to the negative 8. So that's very weak. I mean, yeah, that's very, very weak. So yeah, I looked up Ka and pK values just to see if it could make some more sense of things. Did I just come out of my bitly there? Disaster. Okay, there we go. Lost everything there. Found it again. So happy. Okay, so there's chlorous acid, the HClO2. So that has that's 1.1 times 10 to the negative 2. So, oh, did that all wrong. Let's get the eraser on here. Okay. This here is 2.9 times 10 to the negative 8. So the products of that times that over this is tiny. So this is hardly any breaks apart. But this is up to 1.1, I think, times 10 to the negative 2. I think, let me double check. Are you there? Chlorus. Yeah. So that's saying that almost like 0.001, 1 in 100. 1 in 100 of these will break apart to this. So whereas like 1 in a billion, you know, of these will stay is like this. So for every one, there's a billion of these. For every one, there's 100 of those. But it's getting more likely. It's getting more and more likely that this will sit there. So, oops, let me do this properly. Let me put a 2 there. So this is becoming more stable, and then by the time we get up to HClO3, it's one way. Pretty much all of this breaks apart, and then the HClO4, H posit, they're both regarded as your strong acids. These are strong. So it must be something to do with these oxygens. These oxygens must be doing something. So the theory is that the oxygens, the electronegative oxygens, pull on the central atom, and I think there's pi bonding. We could do the Lewis structure for ClO4 and see what's the Lewis structure for ClO4. This is a good reminder. Can you do that? I mean, this is like classic AP question, FRQ. Draw the Lewis structure for the perchlorate ion. Go, justify the shape, tell me the bond angle. Are these all the same length? So let's see, so let's count 7 plus 4 times 6 equals 24, 31 plus 1, 32. So then the Cl goes in the middle, Cl, and then we do singles. O, 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 O. How many have we used up? 2, 4, 6, 8. Got a lot left. Can I just do this? 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12. Can I do that? So 6 round each, 4, 6 are 24, plus 2, 4, 6, 8, 32. Yeah, that matches up. Everyone should be happy. Don't know if I can be bothered finding the formal charges. Idea here being that these are happy holding, these are very electronegative, they're happy holding the negative, extra negative charge which is on here, distributed across all of them. That's the idea. I don't think you need to know any more than that. And so this, the more electronegative this is, the more stable this is. I guess the thing is, what does the actual acid look like? The acid from this looks like let me keep erasing this here. So the acid's connected to this. So I also think it's interesting. This can also this bond can be broken quite easily. This bond is very easily broken. Why? I guess everything's pulling all the electrons away from it. And so they're pulling all the electrons this way, and then everybody ends up with the same number of electrons, and they kind of stabilize in this tetrahedral shape, right? With lots and lots of electrons around them. But I guess they're happy because this is quite electronegative, and these are all able to support that charge. Don't know if I'm totally explaining that, but that's what the evidence tells us. So that's how, and so it seems that they want you to be able to compare some acids. So let's take a look at one of those. Oh, so there's a good example. Why is H2SO4 versus H3PO4? So these are SO4 versus PO4. This is the phosphate ion versus the sulfate ion, or dihydrogen phosphate ion versus the hydrogen sulfate ion. Why is this strong and this is weak? I guess let's look to a periodic table, see where they are. Oh, great spelling. Periodic table of elements. So the sulfur is more electronegative than the phosphorus, right? So it's further right, it's got another proton on it, and it's able to pull everything in more. And so the rule is this if this sulfate ion is more electronegative, it pulls everything towards it and it stabilizes the ion and it weakens whatever bond is on the SO4. I mean, I presume what have we got here? The sulfate ion and a couple of hydrogens around it. This being more electronegative pulls all the electrons towards it and seriously weakens the bond between the H and the S, or the H and the O that it'll be connected to. And then here, this doesn't weaken the bond as much as this one does. Let's draw a little vector in there. So you might have to compare, as we did in a homework, right? Which is the stronger acid? Use this as your kind of memory. Sulfuric is strong, phosphoric is weak. Why? Because this is more electronegative than this, right? So more E negative, more E negative. Okay. Okay, let's take a look at